All right, so in this next section, we're going to look at 5.5, which is zeros of polynomial functions. What we're essentially going to do, we're going to take the topics and the items that we learned and talked about in 5.2 through 5.4. We're going to start tying all that together into a bigger picture with the addition of a whole bunch of theorems that you guys are going to need to know, some of which are going to be more important to memorize and know how they're used than others, and I will point that out as we go through which ones are absolutely imperative versus which ones are good extra information to know. This video is probably going to be a little bit lengthy, so I would recommend that if you need to partway through, pause it, take 5-10 minutes, step away for a little bit, come back, and work through and finish that video. Okay, again, this is probably going to be a little bit lengthy because there's a lot of stuff I have to cover in here. So first thing we come to is fundamental theorem of algebra. This one here is a nice to know, but it's kind of captain obvious. It says that if a polynomial function has a positive degree, thus meets the definition of a polynomial function, and complex coefficients, then that function must have at least one complex zero. All it's saying is that a zero must exist. Okay, nothing crazy here. It is also allowing for, though, it doesn't have to be a real zero or solution. It can be complex, right? And my coefficients of the function can be complex as well. We are typically going to deal with polynomial functions where we have real coefficients, which would then still allow for the possibility of complex or real zeros, because remember, the real numbers are a subset of the complex numbers. The second one is the complete factorization theorem for polynomials. All right, what it says is that if a function is a polynomial with degree greater than 0, again, just definition, it's a polynomial, then there exist n complex zeros, right? Such that we can write the function in a factored form, some value a times x minus the first 0 times x minus the second, so on and so forth, all the way through the nth factor for my complex zeros. All right. Again, where a is just a leading coefficient, and each of those c sub whatevers is a zero of the polynomial function f of x. So let me put this into less letters and a couple of numbers for example here. So what it's saying is I could write something maybe in the form of f of x equals, I don't know, x minus 2 times x minus 3 times x plus 2i times x minus 2i, and this is some polynomial function where we had solutions of 2, 3, and plus or minus 2i. Okay. Also keep in mind, this is a straight up imaginary number. We can also have the full complex number. So I could have something that maybe is of the form like x minus the complex number, I don't know, let's do 5 minus 3i, right? And then my other factor, x minus possibly 5 plus 3i, okay? Where these are my complex conjugates, and we're going to talk about why I chose complex conjugates here in a minute. But where maybe it's coming in the form of complex conjugates and it is a full complex number instead of just an imaginary component of a complex number, this is also fair game. This would give me solutions then of 5 minus 3i and 5 plus 3i, okay? So theorem on the maximum number of zeros of a polynomial. If I have a polynomial function of degree n greater than 0, then that function has at most n different complex zeros. So if I have a 5th degree polynomial, I can't have 6 different zeros. The most I can have is 5, okay? This is just giving us a cap of the number of distinct different zeros that we can possibly have, right? The next one, and again, that one was kind of a, yeah, it should be pretty obvious. If I have a quadratic 2nd degree, the most I can have is 2 zeros, okay? Second one is theorem on the exact number of polynomials or zeros of a polynomial, or the n zeros theorem. Again, if we have a polynomial by definition, and if a zero has a multiplicity of m and is counted m number of times, then that sum of the multiplicities must equal n, is essentially what this is saying. All right. So if I look here, remember when we talked earlier, anything without an exponent has a multiplicity of 1. Okay. The sum of those multiplicities, because here I'm going to have x equals 2 with a multiplicity of 1, x equals 3 with a multiplicity of 3, x equals -1 with a multiplicity of 2, and x equals -2 with a multiplicity of 5. What this is saying, though, is that the sum of my multiplicities here, right, which would be 11, right, gives me the degree of the polynomial function, which we saw before, and also the degree then in turn gives me the total number of zeros when I count the multiplicities that occur. They don't all have to be distinct zeros or solutions. They can be repeated, and each of those repeated zeros gets counted via the multiplicities for the total number of solutions or zeros and the degree of the function. Okay. Again, that is good to know. We're going to use that a lot. The degree tells me the number of zeros, and when I add up the multiplicities, which is something we'll do to double check that we have everything, that we didn't miss anything, is where that's going to come into play mostly. The next one that we get to here is the theorem on conjugate pairs of a polynomial. So let's say we have a polynomial where the degree is greater than 1 in this case, and it has real coefficients. That's an important one here for this, is that it must have real coefficients. All right. If I have a complex zero of a plus bi, and b not equal to 0, then the conjugate pair a minus bi must also be a 0 of that polynomial function f of x. Has to happen, right? If it doesn't happen, right, we don't get a polynomial with real coefficients. So the key here is the real coefficients, and you may or may not see a problem or two where you're asked to come up with a polynomial with real coefficients, and you have to know this theorem to know that given a complex 0, its conjugate must also be a 0. So let me show this to you. So if I had those zeros that were mentioned there, a plus bi and a minus bi, right? Basic example, if I FOIL all this out, I'm going to have x squared minus x a plus bi minus x times a minus bi, right? I guess technically it'd be in the other order, but it's okay right now. Plus a plus bi and a minus bi, right? So all I did here is I FOILed to get these 4 terms. So now if I distribute, I have x squared minus ax plus bxi, or excuse me, minus bxi, and then minus ax and plus bxi. And if I FOIL all of this out, I'm going to have plus a squared minus abi plus abi and minus b squared I squared. So if I go through, here I have a negative bxi and a positive bxi, a negative abi and a positive abi. And here the I squared equals -1. So if I make that substitution and I combine like terms here, we're going to get the following. I'm going to have x squared minus 2ax plus a squared, and here we're going to have negative b squared times -1 or plus b squared. And notice what is nowhere in this simplified form. There are no more i's left. I have canceled out all of the imaginary numbers, and regardless of the choice of the a and the b and the real number or the complex numbers a plus bi and a minus bi, as long as it is a conjugate pair, I've just proved to you that it's guaranteed that it's going to cancel them out. Okay, so again, polynomial with real coefficients. If I have a complex 0, whether it's a plus bi or whether it's just the bi portion, okay, then its conjugate, either a minus bi or the opposite of bi, must also be a 0. Okay. Next one is the rational zeros theorem. Okay, the part you're going to really need is on the next slide, which is how we're going to use it. But the rational zeros theorem says that if I have a polynomial, f of x equals, and this is just a standard definition of a polynomial, a sub n x to the nth, a sub n minus 1 x to the n minus 1 power, all the way down to a sub 1 x to the first, and a naught, or my constant term. If the polynomial has integer coefficients, and if c over d is a rational zero of the polynomial f of x, such that c and d have no common factor, right, meaning I can't reduce them, then the following two things must be true. The numerator of that rational zero must be a factor of my constant term. Has to be. Absolutely 110%. The denominator of that rational zero must be a factor of my leading coefficient. Okay? And again, like if we sit here and multiply it all out, that has to be the truth. So let me give you a very basic example here. Okay, so if I had this and I FOIL it out, we're going to have 2x squared. Let's see, we're going to have 3x plus 4x, or 7x and plus 6, right? You would agree that my solutions here had to have been 2 and negative 3 halves. Well, both 2 and negative 3 would both be factors of 6, and this 2 in my denominator is a factor of my leading coefficient, 2x squared. Okay, so this works in much larger, much bigger problems as well in the same way. This is just a very simple example of what it's saying. So how in the world are we going to use this? Well, let's take a look. So the rational zeros theorem, or RZT, right, is how I'm going to abbreviate that when we go forward and start using this. We're going to generate a list of all of the possible zeros or rational zeros of my polynomial function based on the following ratio. So I'm going to list the factors of my constant term a naught over all of the factors of my leading coefficient a sub n. And every single combination of those factors, okay, gives me a possible rational zero of the function. It doesn't give me the rational zeros themselves. It gives me possibilities that I then can go and test. All right. This is one of the key things that's going to allow us to be able to go through and test different values in an effort to work towards something that is completely factored and solved, or to get it down to something where we have more, not sustainable, but simpler methods to continue factoring and solving. When we're dealing with something greater than a quadratic, or maybe a cubic that behaves nicely, we're dealing with something that's 4th degree, 5th degree, 6th degree, the rational zeros theorem is going to be your best friend. And as we go through the process and we continue factoring, we're going to continue to essentially reevaluate to an extent, or see if there are any things that are in our rational zeros list that we can eliminate based on what we have left in terms of a factored polynomial. Okay, so when we go through here, all right, let's take a look at the next example, because I think this is probably going to make a little bit more sense once we put one in front of us. So let's say I have the following polynomial: f of x equals x, or 3x to the 4th minus 2x cubed minus x squared minus 12x and minus 4. Okay, it's 5 terms. It's not going to factor by grouping. So what we need to do is we need to evaluate my rational zeros theorem. So I want all the factors of my constant term, negative 4. So I have plus and minus 1 as a possibility. That's a factor. Plus and minus 2 and plus and minus 4. Those are all of the factors of that constant term, negative 4. Now I want all of the factors of my leading coefficient 3. So I'm going to have plus and minus 1 and plus and minus 3. So now what I need to do is I need to go through, right, and I need to come up with all of the possible pairs, essentially with each of my two, in this case, possible denominators. So what I'm going to do here is I'm going to generate a list, right? So I'm going to start with my first denominator, right? The plus and minus 1. It's my easiest case. So this is going to give me each of my individual numerators. So plus and minus 1, 2, and plus and minus 4. Now I'm going to go to my second denominator option, and I'm going to write each ratio over that second denominator option. So now we're going to have plus and minus 1/3. We're going to have plus and minus 2/3, and we're going to have plus and minus 4/3. Okay, these here are 12 possible, because we have the plus and minus for each one, 12 possible rational zeros of this particular function. Now, we're not going to go through and actually factor this one right now. We're getting to that here in a little bit. Okay, but these are all the possible zeros that we can test. Now, again, these can repeat. They can have multiplicities that are higher than 1. So when we go through, just because you found a zero worked, you should probably test it a second time, because this doesn't guarantee that it only works one time. It could work multiple times. Okay, and we're going to talk again more about what things to look for, how we can reevaluate as we go, and continue evaluating the rational zeros process each way along. Right. So let's take a look. The next thing we have is the first theorem on bounds. Okay, first theorem on bounds. This is somewhat useful because sometimes when we do rational zeros, we're going to get some really large lists, and this might be able to eliminate some of those choices and narrow that list down a little bit for us. So suppose I have a polynomial with real coefficients, and a is positive. Okay, a must be positive for this. All right. Positive leading coefficient, and that f of x divided synthetically by x minus c, or divided synthetically by x equals c. Okay, so if that c that I divided by synthetically, right, if c is greater than 0, and if all numbers in the third row of the division are either positive or 0, then c is an upper bound for all real zeros of f of x. So what that means, okay, is that if I synthetically divide in that third row of synthetic division, every number is either a 0 or is positive, then there are no values of that are in my rational zeros. There are no possible zeros that are greater than that particular zero that I just tested. So if I tested, for example, from my list here, let's say positive 2, right? And all that bottom row was all positive values. I know that now I could eliminate positive 4 as well, because 2 would have been an upper bound. That's just an example. I'm not saying that's actually an upper bound for that problem. The second part of this, second case, and this is different if that c you divided by was positive or if it is negative. If c is negative and the numbers of the third row of the division process are alternating positive and negative, then you can count a 0 as either, but then if you have a positive, a 0, then you must have a positive for your next value, because that 0 would have counted as a negative. All right, so they alternate positive and negative. 0 can be counted either way. Then c is a lower bound for that real, for the real numbers or the zeros of that polynomial. And again, what that means, if I tested, say, a -1 and my third row alternates, then anything that is more negative than the -1, so like the -4/3, the -2, and the -4 could be eliminated if I haven't already. Okay, so let's go through and let's take a look. So I want to determine the largest and smallest numbers that could be upper and lower bounds here for this function. So let's go through it first. Let's do our rational zeros theorem and take a look here. So my rational zeros theorem is going to give me, and I got factors of my coefficient or my constant terms, so plus and minus 1, 2, 3, and 6. Now the nice thing here is my leading coefficient is 1, so I don't have to do the denominator of that ratio, and I don't have to come up with all the combination. It's literally just now the factors of that constant term. So what I'm going to do is we're going to go through and I want to look at I want to take a look at some of these zeros. Okay, so let's say that I went through and let's pick 3, for example. All right, so if I want to synthetically divide by 3, right, so I'm testing x equals 3 to see if it's a 0. All right, so I'm going to divide 1, -1, -2, 3, and 6. Okay, so again, synthetic division process, I'm going to drop down that first term. So I have a 1. I'm going to multiply 3 times 1 is 3. I add, I get 2. 2 times 3 is 6. I add, I get 4. 3 times 4 is 12. I add, I get 15. 3 times 15 is 45. And I add, and I get 51. So a couple of things that I see here. First and foremost, 51, my remainder is not 0. Therefore, x equals 3 is not a 0, and x minus 3 is not a factor of the polynomial. But the other thing that I notice is that every single term in my third row here is, excuse me, either positive or 0. So what that tells me, because everything was positive or 0, right, that x equals 3 is an upper bound of my polynomial. So what I could do then is I could get rid of the x equals positive 3 and anything larger, in this case, the x equals positive 6. I don't even need to test positive 6. I've just demonstrated that it can't possibly work. Okay. What I could then do is go through and I could test, say, 2, for example. All right. So we have that there. Let me actually do this beauty of using Notability. I can save this and duplicate it. So here is my demonstration that that was in fact an upper bound. All right, I'm going to go through and I'm going to get rid of the work that I did here because I'm going to redo this with a different 0. So let's try with 2. Okay, so let's try x equals 2. All right, so again, process, I drop down the 1, multiply 2, 1, 2, 0, 0, 3, and 6, and I add, excuse me, and I get a 12. Okay, oops, I just realized I had made a mistake there. This is a -6, and that kind of changes my outcome a little bit there. So I do get a 0 here. All right, so 2 things I want to show you. All right, first and foremost, 1, I get 0 as a remainder, which tells me that x equals 2 is a 0 of my function. And what that also then tells me is a factor of x minus 2, all right, or x minus 2 is a factor of the function, okay? So what I could do is write then x minus 2 times, and what's left here is my quotient, right? So I have x cubed plus x squared plus 0x and plus 3, okay? I could write this now in a factored form, right? If I were 100% done, I could go on from there. Here we still have a little bit of meat on the bone. We still have work to do, although again, we're not going to go through and continue more at the moment in terms of trying to factor and solve. But what I could do then from here is now I could stack another division on right here, and I could say, well, let's test 2 to see if it works again, right? So if we go through, right, I would have the 1, 2, 3, 6, 6, and 12 for 15. So 1 from up here, everything was positive or 0. So I knew that 2 was an upper bound, okay? 2 had to be an upper bound. Okay, but also, think about this. This is the polynomial that was left over after I factored out this original x minus 2. If you thought about rational zeros theorem from here, any of my possible rational zeros have to be a factor of 3 in this case. Therefore, this 2 could not possibly be a rational 0 anymore at this time. So I could have eliminated it from my list over here. Okay, and as we go through this, we're going to continuously go through and check to see what we have in terms of zeros and excuse me, what's possible as a zero of the function at any step along the way, right? The one other thing that I could go through and show here, let's do a negative just so I can show this to you. So let me just pick -2, for example. I know it's not going to work, but let me show what this would look like. So we bring down the 1, we multiply, we add, we multiply, we add, and we multiply, and I get a remainder that's not 0. However, okay, now I had a 0 that I was testing that was negative, and I have a third row of my synthetic division process in which my terms alternate positive, negative, or it could start with a negative, it could go negative, positive, negative, positive. Actually, let me take that back. It can't, because that first leading term has to be positive for this. You would need to factor that -1 out ahead of time, okay? So scratch the fact that I said it could start off with a negative. It has to go positive, negative, okay? But here what I get is that alternation. So what that tells me then is that from here, right, x equals -2 must then be a lower bound of the polynomial function. Now, it doesn't mean that I can't have a lower bound that is in fact smaller. It's just telling me that -2 is a lower bound, okay? So I'm going to move on from here because we're going to do more with this as we go through. Excuse me. As we go through, and hopefully this will make some more sense as we get a little more practice with it. Now, we do have a second theorem on bounds, right? You were probably thinking, well, if they said it's the first theorem on bounds, there had to be a second one coming. First theorem on bounds is more useful. It's more applicable, and we essentially evaluate that every single step of the process. Every time we do a synthetic division, you need to be thinking first theorem on bounds, and whether or not, excuse me, you met the conditions for that first theorem on bounds for that particular zero or not. Second theorem on bounds is helpful when we have large lists and when we have large sets of values from the rational zeros theorem, but it doesn't always give us a whole heck of a lot. So let me go through what it is. All right, so let's suppose we have a polynomial function of the standard definition here with real coefficients. Then all of the zeros of the polynomial f of x fall within the interval -m through m, where I'm going to define m, okay, as the following. All right, so it's going to be the maximum of the absolute values of each of those coefficients. So I'm only looking at the positive values here. Okay, so whatever my largest coefficient is, divided by my leading coefficient. And then I'm going to add 1 to it. So again, we're going to have the largest coefficient divided by the leading coefficient, and I'm going to add 1 to it. And what that's going to give me then, whatever value I got for m, everything must fall in the interval of -m to m. All right? So once we have our rational zeros list, we can take a look at the second theorem on bounds. There's sometimes I skip this, okay? But we can take a quick look at it and come up with that interval -m to m and see right off the bat, again, are there any values that I can scratch off my list right away? So let's do an example real quick. So here I have the second theorem on, or the following function to evaluate the second theorem on bounds. So let's do rational zeros theorem, right? So again, factors of my coefficient or my constant, plus and minus 1 and 5 in this case because it is a prime number. And then factors of my leading coefficient are going to be 1 and 3. So now here, because I have multiple different possibilities for my denominator, I must come up with my list. So my list then is going to be plus and minus 1, 5, 1/3, and 5/3. Okay, so now what I want to do, right? I'm going to evaluate second theorem on bounds. So again, I need to determine what m is going to be. All right, so m is going to be my largest coefficient, which in this case is 6, divided by my leading coefficient, in this case, which is 3, plus 1. So here I get 2 plus 1, or m equals 3. So what this then tells me is that everything must fall in the interval from -3 to 3, okay? And that interval is non-inclusive, okay? So what that tells me then is right off the bat, I can get rid of this plus and minus 5. I know from the second theorem on bounds that plus and minus 5 can't possibly be solutions of this particular polynomial. Okay, again, I'm not going to go through and solve this one. I don't know for a fact that it solves nicely. Okay, these are just ones I have for example right now. All right. Next thing we have, right, and again, this one here is a kind of nice to know, but not necessarily one that we're going to use and have to be able to quote, like rational zeros, first theorem bounds, and second theorem on bounds for that matter. You need to know, and you need to be able to know how to use and apply them. Okay. So every polynomial with real coefficients and a positive degree can be expressed as a product of either linear or quadratic factors with real coefficients such that the quadratic factors are irreducible over the reals, right? So what that means is any of those quadratic factors then would have complex zeros or complex coefficients if you broke them down any farther. All right, but what we can do is for every single polynomial function, there does exist some product of factors such that all those factors are either linear factors or quadratic factors, and quadratic factors that would break down into complex factors. Again, just saying essentially that we're able to do that, and we're going to break things down to either linear factors or to quadratic factors, and then we can solve those quadratic factors with a quadratic formula or something like that to go from there. All right, so factoring polynomials. So here is kind of my guideline steps that we're going to follow to factor and solve polynomial functions. So we're first going to use the n zeros theorem just to figure out the number of zeros that I'm looking for. Now the second one here that I have listed, okay, I haven't even gone over this yet because it's a lot of work, and really it doesn't give you a whole lot of results. It's kind of wishy-washy, and I'll probably make a separate video on Descartes' rule of signs. But depending on what you have, you can determine the number of sign changes and then apply Descartes' rule of signs, which will give you possible combinations of how many positive, how many negative could you have, but it gives you multiple different possible combinations. And again, it really doesn't help us out directly a whole lot. All right, so the next one we're really going to use is the rational zeros theorem. We're going to come up with that list of possible zeros. We're going to apply the second theorem on bounds to eliminate zeros from that list. Second theorem on bounds, one other note about that is if we have relatively small coefficients for all the terms, second theorem on bounds is probably going to eliminate a lot of stuff. However, if we have some really large coefficients in there, it is very possible that we don't really actually eliminate anything with bounds, okay? So again, I usually make a determination whether or not it's going to be helpful, or I do it very quickly in my head to see if I can use it or not, right? From there, then, we're going to start testing possible zeros using synthetic division. Once a zero has been found, we're going to stack a synthetic division right underneath of the quotient that we just got. And I'm going to continue trying to factor the new quotient until we get down to a quadratic, which I already know how to solve with quadratic formula and other methods, okay? If you find that a particular zero works, so let's say you find x equals 2 works, I want you to immediately, with the quotient that you have, I want you to try x equals 2 again, because it might work multiple times. I want you to try it again and again and again until it no longer works. So once you find a zero that works, I want you to test it again and again. And if it factors, test it again. If it factors, test it again until you get a remainder other than 0 and it didn't work. Then cross it off the list and continue on as appropriate, okay? And you're going to use, like I said, synthetic division until you get to something with a second degree, okay? Once you test a factor that doesn't work, you can go ahead and eliminate it from your list. You can erase it, you can cross it off, whatever's going to work for you, okay? I tend to start with the plus and minus ones and, the plus and minus twos, and I kind of work my way out from 0. A couple of reasons. One, they're usually easier numbers to work with. 2, sometimes they just happen to be factors that work, Okay, not always, but sometimes they do, right? If I know I have a, say a 3x to the whatever power out in front, I know I've got to have, whether it's a 1/3, a 2/3, a 4/3 as a factor. I typically wait until I get down to something smaller before I start testing fractional rational values, just because it makes my life a little bit simpler as I go through. Okay, so what we're going to do is we're going to go through and we're going to factor and solve a couple of these functions. Okay, so let's take a look, and I'm going to come back and we'll look at that one here in a bit. So let's come down here to f of x equals x to the fourth plus 3x cubed minus 30x squared minus 6x plus 56. So n zeros, this is going to tell me I have a fourth degree polynomial. So I'm looking for 4 zeros. Okay, rational zeros theorem. I want factors of my constant. So we're going to have plus or minus 1, 2, 3 no, 4, 5 no, 6 no, 7, 8, 14, and 28, and 56. Okay, and let me just take a moment and make sure I didn't miss any of our zeros, and I don't believe that I did. Okay, so at this point, excuse me, I'm going to look at theorem on bounds, second theorem on bounds. So 56 is my largest, so 56 over my lead coefficient 1 plus 1, so it gives me m equals 57. So everything has to fall between 57 and negative 57. So it really, in this case, is completely pointless. It doesn't help me out in the slightest. Okay, so what I want to do at this point is I want to go through and start testing some factors. So I'm going to be dividing, right? No missing terms in this case. So 1, 3, negative 30, negative 6, and 56. Okay, if you're not good at mental math yet, you're about to be. All right, as you're going to be going through, you're going to be doing some of these. If you get some nasty, crazy numbers, you probably want to have a calculator somewhere nearby so that you can check your math or use it as you feel you need to. So let's start off. I said we usually like to start with 1 and negative 1 to test. So let's try 1, right? So if I test a value of 1, so I'm going to drop down, I'm going to multiply. I'm going to add and multiply and add and multiply, excuse me, and add and multiply, and we're going to get something that is obviously not going to be 0. So I know that 1 is not a factor of the polynomial. So positive 1, that can be eliminated off my list over here in the rational zeros on the right. Now I also want to take a look before I erase and look at this line here. 1 was positive, so I'm looking, are all values either 0 or positive? They're not, so 1 is not an upper bound. So there's nothing I can do with that. So what we're going to do is we're going to erase this. Okay, and this is one of the places where having notability and the ability to do this digitally is nice. You just erase it. I don't need to erase the rest of it. I just need to erase that work. Let's try negative 1. So negative 1, we're going to go through. So I got 1, negative 1, 2, negative 2, negative 32, 32, 26, negative 26, and 30. So again, here I had a negative value. I know my remainder is something other than 0, so I know this isn't going to work. Negative 0 that I tested, I did not alternate positive, negative. I went positive, positive, then negative. All right, so I know that this is not a lower bound. So again, I'm going to go ahead, I'm going to erase this work that I have here. Okay, and let's try, and I can now erase negative 1 altogether. All right, it went away. I know it doesn't work. Let's try 2. Okay, so let's multiply through with a 2. So I have 1, 2, 5, 10, negative 20, negative 40, negative 46, negative 92, and a negative number. Okay, at this point, it doesn't even matter what the negative number is. I know it's not 0. Really, at this point, I just need to know if it's positive or negative. This was positive for my 0 that I tested, so I would have to look for everything positive or 0, which is not the case. So 2 is not an upper bound. I know 2 didn't work, so I can eliminate it from my list. And let's get rid of the work so we can try our next value. Okay, and you're probably saying, well, when the heck are we going to find a 0, right? Sometimes you're going to test multiple values, and sometimes it's going to take a couple minutes till you find one that works. I'm going to continue on with the positive values here. So let's try 4, right? So I'm going to use the 4, so I'm going to bring down the 1. I'm going to multiply. I'm going to add. Hey, 4 worked. Okay, so since 4 worked, I know that x minus 4 is a factor of the polynomial. And I'm going to write that out to the left there so that I know that that was a correct factor for my polynomial. So what I'm going to do is I'm going to stack a division right underneath of that quotient that I just found. Okay, and now I'm going to test. I'm going to test 4 again to see if it works a second time. Okay, so I'm going to bring down the 1, multiply. Okay, so as I go through, I multiplied 4 times 44. At that stage, it was my second to last term. It's going to be a big number. And I'm going to have a big number plus a smaller negative number. I'm going to have another big positive number. So 2 things that it does actually go through and tell me here is, 1, 4 doesn't work a second time. So I can get rid of 4 from my list of possible values. But it also tells me I tested a positive factor. I got an all positive or 0 third row, which tells me that every positive value greater than 4 is not possible because 4 is an upper bound of the function. Okay. Now the other thing, and I didn't do it here, but let me also talk about it. So I'll get rid of the work here for a second. If we look, because there are other values I can eliminate at this point, right? My lead coefficient's still 1, so I don't really have to do anything with that. But if I look at my constant term now and what I'm trying to factor, what's left over that needs factored, is 14. Any values that are not a factor of 14, thus 8, 28, and 56, can now also be eliminated from my list. Okay, I can get rid of them because I know that what I need to factor still, right, still has to evaluate the rational zeros, has to be true. So if it's not a factor of this 14, it's not applicable in my list of values anymore. So for the sake of trying to get through this a little bit faster than spending 20 minutes on it, I'm going to go with a factor I know works. We're going to try a 0 of negative 7. So I'm going to drop down to 1. Pardon me. I'm going to multiply. I'm going to have negative 7, 0, 0, negative 2, and positive 14 for a 0. So that tells me, I'm like losing my voice all of a sudden here, that negative 7 is a 0, and x plus 7 then is a factor. Now notice that here I have a squared term, x to the first term, and a constant term. Okay, I've gotten this down now to a quadratic factor. So what I've got is, I can write this as x minus 4 times x plus 7 times, and from this quotient that's left over, x squared minus 2. Still all equal to 0. This is a factored form of my original polynomial. And from here, what I can do is I can go through and find the rest of my solutions. So here I'm going to have x equals 4 as a solution with a multiplicity of 1. X equals negative 7 as a solution with a multiplicity of 1. And from x squared minus 2, I'm going to have x equals plus or minus the square root of 2, each with a multiplicity of 1. I'm going to write it like that because I put that plus or minus there to save time. So what I can do is I can go through and sketch this function now. right? It was fourth degree with the A value that was positive, so my end behavior has to be up and up, right? Right? I have zeros at -7, and I'm just sketching where these might be. All right, so at -7, I've got a 0. I've got a 0 at +4, and plus and minus the square root of 2, which is, what, 1.41. Again, I know my end behaviors were up and up. I know I have a y-intercept at +56, which is going to be way off the graph, so I'm not even going to bother to sketch that in. And maybe I get one other thing, because these were all multiplicities of 1, I cross at every single point. There are no points at which I touch and go back. So here I'm going to cross, go way up somewhere, cross, and end up above here. Okay, so I get a graph that maybe, or a sketch of a graph that maybe looks something like this from this function. Okay, we've just solved our first polynomial function. Again, sometimes these are going to take 2 or 3 minutes for a problem, or you might spend 10, 12 minutes on a single problem until you're done, until you've tested and factored everything that you need to go through and test and factor. Okay, let's do 2 more for the video. Okay, so let's take a look at my next one here. So I have f of x equals 12x cubed plus 8x squared minus 3x and minus 2. Okay, so if I go through, right, n zeros tells me it's third degree, so I want 3 zeros. All right, rational zeros tells me factors of my constant term divided by factors of my leading coefficient. And if I go to come up with all of the possible values this gives me, this is going to get interesting. So we're going to plus and minus 1, plus and minus 2. We're going to plus and minus 1/2, and we would have plus and minus 2/2, which is just 1, so I don't have to write it twice. Then we're going to have plus and minus 1/3, and plus and minus 2/3. Then we're going to have plus and minus 1/4, and plus and minus 2/4, which is 1/2. Then we're going to have plus and minus 1/6, and plus and minus 2/6, which is 1/3, which I've already written down, and plus and minus 1/12, and possibly plus and minus 2/12, which is 1/6, so I don't need to write that one twice. This is my list of factors. Okay, I've got a lot of fractions here. Now, let me go back to something I haven't mentioned yet in this video. Remember, whenever we're solving any polynomial, not just quadratics, any polynomial, we always want to look, do we have a GCF? Well, in this case, no, I don't. The second thing I want to do is I always want to look, do any of my simpler factoring methods work? Okay. If I look at this one, it's a cubic, so none of my quadratic factoring methods are an option. However, it does have 4 terms, so I can look to see, can I factor by grouping? Right? Do I have a GCF in the first pair? In this case, I do. It's 4x. Well, let's see. Do I get 3x squared plus 2x? Okay. And actually, let me go back here. It's not just 4x. It's 4x squared, which is then going to give me 3x plus 2. And if I factor out of my second pair a -1, I get a 3x plus 2. This factors by grouping. So here we get 3x plus 2 times 4x squared minus 1. And if I continue solving, I'm going to have solutions of x equals -2/3 with a multiplicity of 1, and we're going to have x equals plus and minus, let's see, we're going to have plus and minus 1/2, right? If I take 4x squared minus 1, 4x squared equals 1, x squared equals 1/4, and x equals plus and minus 1/2, okay? Again, each of those with a multiplicity of 1, okay? So again, think about end behavior here. Degree was 3, A was positive, so end behavior is going to be down and up. I cross at each of my 3 solutions, or zeros, and those zeros occur at -2/3, at -1/2, and at +1/2. I have a y-intercept at -2, and I'm going to end up with a function that maybe looks something about like this. Okay, again, not drawn on graph paper, not necessarily to scale, but for right now, it's going to give me a pretty good idea of what this picture should look like. Okay, let's come down to our next example. All right, so I have f of x equals 2x cubed minus 3x squared minus 17x plus 30. Right? If I look at it, there's no GCF. If I look to see, can I factor by grouping? In this case, it's not going to work. N zeros, it's third degree, so I'm looking for 3 solutions. So let's go right to my rational zeros theorem. So we're going to have plus and minus 1, 2, 3, 5, 6, 10, 15, and 30 all over plus and minus 1 and 2. So again here, I'm going to get all of my individual factors and then all of the fractions. So we're going to have plus and minus 1/2. 2 halves is 1. We're going to get plus and minus 3 halves. Plus and minus 5 halves, 6 halves is 3, 10 halves is 5, plus and minus 15 halves, and 30 halves would be the 15. So again here I've got a really extensive list. Let's do our second theorem on bounds. Okay, second theorem on bounds, my largest coefficient is going to be 30 divided by my leading coefficient, which is 2 plus 1. So here I'm going to get a 16. So everything must fall between -16 and 16. Doesn't eliminate a whole lot, but it gets rid of the plus and minus 30s. Okay. So here, if we start off, and let's just start positive, I have no missing terms, so I'm dividing 2, -3, -17, and 30. Okay. So let's try 1. I always like to start with 1. So here we're going to drop down 2, multiply, I get 2, I add -1, multiply, I get +1, I add, I get -16, and I multiply, I get -16, and I get a +14. Okay, I divide it by a positive value. I know it didn't work because my remainder is not 0. And first theorem on bounds, I evaluate or look at that last line. They're not all positive or 0, so 1 is not a bound for us. Let's take a look. Let's try 2, right? And I can get rid of +1 from my list. All right, so let's try it. So I drop down, I multiply. I add, I multiply. I add, and I multiply. And I add, and I do in fact get a remainder of 0. So again, this tells me now that x equals 2 is a factor, and that x minus 2 then would have to be a 0. Now, again, here my quotient has 3 terms, so what that means is that it's a quadratic. It's 2x squared plus x and minus 15 equal to 0. From here, I can now try and factor and solve this, right? You could try brute force, all right? But I want to look here, A times C method, all right? A times C is going to give me negative 30. Factors of negative 30 that add to positive 1 are going to be 6 and negative 5. Right, so I'm going to factor by grouping here. All right, GCF of the first two is 2x times x plus 3. GCF of the last two is negative 5, and I have x plus 3. All right, so when I get this completely factored, I have x minus 2 times x plus 3 times 2x minus 5. This is going to give me solutions then of x equals 2 with the multiplicity of 1, x equals negative 3 with the multiplicity of 1, and x equals 5 halves with the multiplicity of 1. Again, end behavior, A was positive, degree was 3, so it's going to be down and up. All right, at none of my points in this case, all multiplicities of 1. So I'm going to cross at each point, right? Each of my zeros are going to be at negative 3. They're going to be at 2. And they're going to be at 2.5 or 5 halves. My y-intercept is somewhere way up at 30, right? So I'm going to get a graph that maybe looks something about like this, okay? What I want you guys to do is come back in the notes here to this very first one, all right? I want you to give it a try. See what you can come up with. See if you can factor that one. And then tomorrow in class, okay? Tomorrow in class, we have quite a few other examples that we're going to go through and we're going to talk about, all right? I will also talk about Descartes' rule of signs, how it's used, when it's used, and why I really am not going to focus a whole lot on it because of the pros and cons and what it actually gives us in terms of answers. All right, so again, my apologies for the fact this was a slightly lengthy video. All right, give that other one a shot, see what you can come up with, and we'll see you guys in class tomorrow to do some examples and answer some questions. Have a good night.